We will start our lecture by presenting binary trees. So binary trees are a special case of M-array tree when M is equal to 2. So we say binary tree is a 2-array tree such that every vertex has at most 2 children. Moreover, since the maximum number of children are 2, if we have 2 children, then each child is designated as either left child or right child. Now for a full binary tree, remember that when we say an M-array tree is full, we say an M-array tree is full if all internal vertices have M number of children. So a full binary tree is a binary tree such that every internal vertex has exactly 2 children. Or we can say that each vertex either it has 2 children or 0 children, which are leaves. We will solve 2 problems on binary tree as a theorem. First, we will solve if we have a tree that is full binary tree with I internal vertices, then T, which is the tree, has I plus 1 terminal. Now when we say terminal, it means a leaf, which is a vertex of degree 1. So it has I plus 1 terminals and it has 2I plus 1 total vertices. Let us prove this theorem. So how are we going to start the proof? Here it says that T is a full binary tree with I internal vertices. And we know that if we have full M-array tree, we have 2 equations. The first one is that the number of vertices n is equal to mi plus 1, and number of vertices is equal to I plus L, and L is the number of leaves. So we will start the proof by saying that since T is a full binary tree with I internal vertices, then we will have 2 equations, n equal to 2I plus 1 and n is equal to I plus t. Now here I have replaced m by 2 because it's a binary tree, and I have replaced L by t, which is a terminal. So a terminal is in fact a leaf. Now we need to say what are n and t. So we will say where n and t are the number of vertices of T and the number of terminals of T respectively. So the first equation is already found now, because this is what the question is asking to prove that the number of vertices is equal to I plus 1, so we have found it. Now we need to prove that the number of terminals is equal to I plus 1. So here we will say since n is equal to I plus t, so t is equal to n minus I. And n already we have its equation, which is this equation, so substituted. And so we will have 2I plus 1 minus I, and here we will have I plus 1, and this will complete the proof, because we need to prove that T is equal to I plus 1. For the next problem, it says if we have a binary tree with height h and terminal t, then the number of leaves, which is the number of terminals, will never exceed 2 to the power h. So that means this is like the maximum value we can get for the number of terminals. So how to start the proof? Here we will say the proof. So let us see what is given in the problem. It is given that it is binary. Since it is binary, then m is equal to 2 if it is an M-array tree, and has height h. So h is given as a height and t is given as a terminal. Now if we have an M-array tree The question is, when we are going to have the maximum number of vertices if we have M array tree? We will have the maximum number of vertices if it is complete, so that every internal vertex has M children and all leaves are at the same level. So here we will say that for any M array tree, it will have the maximum number of vertices when it is, here I will write in a different color, when it is complete. And n is equal to m to the power h plus 1 minus 1 over m minus 1. Now we have a binary tree. So since T is a binary tree, then n is equal to 2 to the power h plus 1 minus 1 over 2 minus 1. So therefore n is equal to 2 to the power h plus 1 minus 1. And this is equation number 1. Also, since T is full because it's complete, then we have n is equal to 2i plus 1 and n is equal to t plus I. And t is the number of terminals and I is the number of internal vertices, where n and I are the number of vertices of T and number of internal vertices of T respectively. Now, since n is equal to T plus I, then I is equal to n minus T. Also, since n is equal to 2i plus 1, so here we will substitute for the equation of I into n, and this will be equal to n equal to times n minus T plus 1. Then we will do simplification. N is equal to 2n minus 2t plus 1. Now if you rearrange the equation, so here you have 2n, so take this n this side and minus 2 multiplied by t plus 1, take it to the other side. So we will have, so 2n minus n is equal to t minus 1, and therefore n is equal to t minus 1, and this is equation number 2. If you go back and see what is equation number 1, this is equation number 1 and for n, and this is another equation for n. So we make them equal, so we can say from 1 and 2, we make them equal. We say that 2 to the power h plus 1 minus 1 is equal to t minus 1. So minus 1 with minus 1 will go together, and we will say that t is equal 2 to the power h plus 1 over 2, and this is equal to 2 to the power h, because if you take 2 up, then it will be power minus 1, and also 2 to the power h plus 1 minus 1 will be 2 to the power h. But remember now, the t here is the maximum number of terminals when it is complete, when the tree is complete. So if the tree is complete, then the number of terminals maximum will be equal to the power h. Then here what we can say? We can say for any binary tree, the number of terminals will be less than or equal to the power 2 to the power h, which is h is the height of the tree. And this will complete the proof.